Hello and welcome to our lab on specific heat. Today we're going to be measuring the temperatures and the change in temperature of several different objects. And so temperature, when measured in kelvins, is directly proportional to the average kinetic energy of the molecules that are within a substance. It's not the kinetic energy, but it's a number that's related to the kinetic energy. When we talk about energy, this a transfer of energy from one object to another, we use the word heat, Q. And it has units of joules. And so you can tell here that you actually are talking about energy. And so when you heat a substance, in other words, transfer energy to a substance, you're going to increase the kinetic energy of the individual molecules. They're going to speed up, and their temperature is going to increase. And so that's related by this equation. Q is equal to mc delta T, where delta T is the change in temperature, m is the mass of the substance in kilograms, and C, you can see if we solve for C is equal to Q divided by m delta T, and it has units of joules per kilogram degree centigrade. This means that C is a measure of the number of joules, the energy required to heat 1 kilogram of an object by 1 degree centigrade. For example, the specific heat C of water is equal to 4,186. This is water at a certain temperature. Joules per kilogram degree centigrade. What that means is, if I have a kilogram of water, basically a liter of water, and I want to increase its temperature by 1 degree, then it's going to take 4,186 joules to do that. A kilogram of a different type of material, it may require less energy or more energy to heat that material by 1 degree. So that material would have its own specific heat that wouldn't be the same as the specific heat of water. Now here in front of me on the table I have different metal samples and some water. Actually in these 2 cups I have water that's at 2 different temperatures. And I can get the mass of the water by massing it here. I can measure the initial temperature of the water, and when I mix these 2 different temperature waters together in the styrofoam container, they will come to some equilibrium temperature. And the reason that happens is when you have 2 different substances that are at different temperatures, and they come in contact with each other, and there's going to be a transfer of energy from the object with a greater temperature to the object with a lower temperature. And so the hotter object, the one with the higher temperature, is going to lose internal energy. The cooler object with the lower temperature is going to gain internal energy. But according to the laws of conservation of energy, if my system is closed, there's and energy is conserved, then the internal energy lost by the hot object is equal to the internal energy gained by the cold object. And that transfer of energy, which we call Q, the heating of the object, works like this. So we have m C delta T for the object 1. So we have this, let's say this is our hot object, mass 1. It has a certain specific heat, and its delta T is going to be a change in temperature. This is going to have a situation where the final temperature is lower than the initial temperature, and so this is going to have a negative delta T. And so Q here is going to have a negative value indicating the direction of the transfer. Now, so we'll add that to M2, the second object. It has a different mass and maybe has a different specific heat, unless you're doing water to water. Maybe it has, and it's going to have a different change in temperature. And so this change in temperature has a higher final temperature than its initial, because this is the object we're heating. But when you add up mc delta T for the hot object that's cooling down, mc delta T for the cool object that's heating up, the total change in energy for this closed system is going to be 0. Now this doesn't really happen in real life. We're using open cups and styrofoam containers, and our method of calorimetry is really pretty poor. And so we're actually going to get an overall loss in energy. So there will be some error associated with this experiment. However, we're going to use this basic relationship to make our predictions. We're going to say, assuming that no energy is lost, I predict that my change in temperature for this object is going to be, and then I mathematically make my prediction. And so that's something that you should be able to do. So this lab is basically 3 different activities. In the first activity, you have water of different temperatures that you're going to mix together in a styrofoam container. Knowing their initial temperatures, knowing their masses, you should be able to predict the final or the equilibrium temperature that these objects come to. Once these objects reach an equilibrium temperature, there's no more transfer of energy that takes place. And so they'll remain at that temperature. Of course, it will slowly, cool down to room temperature after that, because this is not a closed system. But if you measure your change in temperature, fairly quickly, give it a quick stir, make that change in temperature happen, and then record your values, your final values, you should hopefully be able to predict, using this idea of conservation of energy, the final temperature of that water mixture. In part 2, we're going to take an aluminum sample. It's the long sample, and we're going to heat it up. You can heat it up by submerging it in a cup of hot water. Make sure that the object doesn't touch the sides of the container, and make sure that it's completely covered with the water. That way, the temperature you read of the water is going to equal the temperature of the sample. And so now let's say we have some room temperature water in this styrofoam container. Well, I take that hot sample, try to get rid of the water, and I dunk it in the room temperature water. Well, there's going to be a transfer of energy from the sample, from the aluminum, to the water. So I can stir around with my thermometer and it will reach some final temperature. And so knowing the mass of the water, the mass of the sample, be careful that you don't include the mass of the styrofoam in that water mass. You'll have to subtract that out, right? And so knowing these masses, knowing the initial temperature of each, you should be able to determine what that final equilibrium temperature is using the conservation of energy. You'll do this again with an unknown sample. Here are some unknown samples that you could use. And with 2 of these samples, you're going to be designing an experiment in which you determine the specific heat of the sample. So before, you knew what the specific heat of aluminum was. You knew what the specific heat of water was. But in this case, let's say you have an object you don't know what the specific heat is. You're going to have to do this experiment, observe a change in temperature using the thermometer to define the initial and final temperatures of all these objects. And set up your experiment so that the only unknown after you perform the experiment is the specific heat of the object, which you can then calculate. And so that's going to be an experiment that you design. And you'll retry it on at least 2 of these objects. So good luck with that, and I hope you enjoy our lab on specific heat.